Hey folks, welcome back. So last episode we talked about digging into the depths of theoretical level of a simple linear regression model. Specifically, we generate some random x and we're building a theoretical model that we know what is the true parameter, and we simply just build a linear regression model from scratch using matrix algebra, and we figure out what is the most optimal parameters, theta best. So with that being said, let's dig a little bit more deeper to see if there's some other methods allow us to arrive the most optimal parameter. So this episode, we're going to be talking about gradient descent, specifically gradient descent. So let me make a markdown box, gradient descent. Specifically, gradient descent is talking about the following. First, we need to define the loss as L2 loss. So this is going to be essentially called mean square error. And it's defined as summation y hat minus y square and divided by n. So that's going to be a fraction y over n. Boom. So there you go. That's our loss function. When we fit the model, we have some sort of educated guesses. The educated guesses will give the name, right? Let's call it y hat. This y hat we're going to compare with the real values in our training set. And that tells us where our mistakes are. Hence, the concept of loss. This is going to be extremely important because it actually guides us to a direction to tell us what is the way to change, to update our beliefs of the parameters so that perhaps we can make more accurate, more precise, educated guesses y hat. So how do we do that? We need to take the gradient with respect to your beta. So let's write that out. Gradient of loss, I'm going to say grade of mean square error, and then that's going to be 2 over m, and then in here it's a matrix algebra, so that's going to be x transpose x theta minus y. Boom. So essentially what's happening here? Oh, I missed equality sign. So what's happening here? This is essentially you take the partial derivative with respect to the theta term. And in this case, theta is the parameters. So 2, if you take partial derivative, this 2 comes forward. Hence, you have a 2 here. And whatever's in between, this y, it's actually x theta. And that's by chain rule. So let's write this out. This essentially come from take partial derivative of MSE with respect to theta. And the first thing you do is you take this partial derivative. So we're going to say partial over partial theta. And that's going to be your MSE. And that's going to be 2 comes forward, right? So fraction 2 over n. And whatever's in the middle, we have educated guesses. So we're going to say x theta minus y. We need to put a parenthesis. Oops. We need to put a parenthesis, and the 2 disappears. But then here, we need to have chain rule of this part. And I'm going to write that yes here. Partial theta here. And then, and by chain rule, we arrive with the following. I made a mistake somewhere. Let's try figure that out. There's one more bracket. Boom. Okay. So take partial derivative of this loss function with respect to theta. 2 comes forward, and I have another typo here, and the 2 disappears from here, and then we have this chain rule in here that we need to take out and take a derivative again, and that's why this x come up from, and that's why this x transpose show up here. So now we have the setup. Based on this model, we can update our parameters. So here we're gonna say gradient descent algorithm is essentially you update your theta. So here we say theta new, and that's going to be defined as your old theta minus eta, which is a learning rate, like a small step, c dot, the gradient of MSE, while eta is learning rate. Okay, so with that being said, let's code this up. We set eta to be some small number, say 0.1. We have n iterations, right? Because this is technically speaking within a loop. So we're gonna say while algorithm converge, we do this. So n iterations, let's say 1,000. And m, let's say 100, right? Because that's essentially the total sample size that we did. I believe it's up here. Aha, 100. So that's why this is 100. Now we call the gradient descent algorithm. So we're gonna define a function. We need some sort of initialization, right? So the theta here, the first step is actually randomly generated. So we're gonna put a remark. At the very first iteration, theta is randomly generated. Okay, so we're gonna say theta, and that's going to be np random from normal distribution, and now we're gonna give it a size. And let's start our algorithm. So for iteration in range of n iterations, what we're going to do is we're going to calculate gradients first. And specifically, that's going to be 2 divided by m times this X matrix, XB, transpose, and we're going to do a dot product of XB dot theta, and then we're going to minus y in the parentheses. And so once we have the gradient, we will update our theta. And this theta here, we don't want to call a new name because we want to override whatever this is. So theta is going to be theta minus eta times gradients. So let's hit it. Boom. What is the problem? N iterations. N iterations. Oh, did I run this? N iterations. There we go. That's the typo. Boom. So that's done. Let's print that out. Okay, so it's 2.01 and 3.03. And as you can see, this result is very similar to what we have up here from the linear model and what we have up here, the basic linear algebra from scratch. So there you go. I hope you liked today's episode. If you want to support the channel, give it a like and hit that subscribe button, and I'll see you in the next episode.